All right, let's carry on. So we are going to talk about Carnot's theorem. Before we talk about Carnot's theorem, let me represent schematically what a Carnot engine looks like. So a Carnot engine, works between two temperatures. Okay. So we have some hot temperature TH, and we have a heat reservoir. So something which is like always at a fixed temperature TH, so that if you hook up something to it at a lower temperature, heat is going to start flowing. And then we have a reservoir at a lower temperature TC, which is T cold. So TH is greater than TC. We haven't, and then we have a Carnot engine which has all these Carnot cycles, reversible cycles, hooked up between these. So there's this is the Carnot engine. And what the Carnot engine does is that it's a reversible engine. So usually it takes in heat from the hot thing, and then it dumps heat into the colder reservoir, and it converts the difference of the heat into work. Okay, so this is a reversible engine, so we can change the direction of the work. If you change the direction of the work, then it'll dump heat into the hot reservoir and absorb heat from the cold reservoir. All right, so now Carnot's theorem. Oh, in the last class, we also introduced the idea of efficiency for a Carnot engine. So eta, which is a function of the hot and the cold temperature, is given by work divided by QH. So this is called efficiency. And basically what it is saying is that, given how much heat I can absorb from the hot reservoir, how much of that can be converted to work, because we know that heat is a form of, is a way of transferring energy. Wouldn't it be nice if we could convert all that heat into work? What do you think? That would be very nice, right? Then we would just we would not have any waste whatsoever. We would just be perfect. Like we will be like, yeah, it'll be like paradise. But it turns out that's not possible. Because we know that Kelvin told us, according to the second law of thermodynamics, we cannot turn a certain amount of heat solely to work. So therefore, eta will be always less than 1. Okay. So what is Carnot's theorem telling us? Carnot's theorem is saying that suppose we have an engine which is not a Carnot engine, which is not a reversible engine, then its efficiency will be less than the Carnot engine. Okay, so Carnot's theorem states that of all the heat engines, so any engine that acts as, in terms of drawing its energy from a heat reservoir, of all the heat engines working, say, between two temperatures, the Carnot engine is the most efficient. Okay. So this is the theorem. Sorry, let me just make sure I'm not missing any questions. All right. Okay. No new questions. Okay, let's prove this, okay? And I think that should be enough for today's class. So, okay. So proof is by contradiction. Okay, let's assume that such an engine exists. Let's assume an engine exists that is better than Carnot. Okay, and whose efficiency is greater than Carnot. So let's do something. So we have some TH. So T of H, and then there is, say, TC. And let's call this engine E. I don't know why. And so suppose this engine draws Q prime H heat from the hot reservoir and gives up Q prime C heat to the cold reservoir and gives out heat, gives out work. And we use that work because Carnot engine is a reversible engine. That little thing that we drew. We can run it backwards, right? We can run it backwards, and if you run it backwards, then it's going to take in heat here and dump heat here on the cycle. So that means it'll dump heat onto the hot reservoir while it takes in heat from the cold reservoir. Okay, so this is Carnot. Okay, so we are assuming that the work from the first engine is greater than W by QH. Okay. So, but we know that work is Q prime H minus Q prime C. And of course, that is equal to Q of H minus QC. Okay. So here, these are all positive quantities, right? Their direction is just telling me whether they're being absorbed or dumped. Okay, so now so what is this inequality now telling us? It's telling us we can, we can then that Q of H is greater than Q of H prime, right? That's what it's telling us. And then this equality, so from this inequality we get this, and from the equality we get Q of C is greater than Q of C prime. Okay. So, this Q of H minus Q of H prime is the amount of heat dumped into the reservoir TH, right? It's dumped into the reservoir TH. Whereas Q of C minus Q of C prime is the heat extracted from TC. So what we can now do is that we can now like consider this to be one machine. Then what we have shown is that if an engine exists whose efficiency is greater than Carnot, then we can we can convert, we can take heat from a cold reservoir to a hot reservoir without any other effect, right? And that is something that violates the second law of thermodynamics. And therefore, our original assumption that there exists a machine that is more efficient than Carnot must be wrong. Okay, so that's Carnot's theorem. Carnot's theorem tells us that Carnot's engine is the most efficient engine there is. Okay, any questions?
Sir, before you end discuss, will you please summarize the whole lecture from the beginning?
Right. So at the beginning, we I don't know, were you there for we mostly talked about calculus. We talked about the second, we basically talked about, when we have functions of more than one variable, we have a choice in how we take the derivatives. And we talked about what the geometric interpretation of d of u is. D of u is the change in u in some specified direction. And then we talked about how that was related to the gradient of u and a bunch of other stuff. Sorry, Farhan, is that you who asked this question? But I was just wondering if you were there for the whole lecture.
I came after 20 minutes.
Okay, so is that why you asked me to review that?
Yes, sir.
Okay, why don't you, because I'll be posting this by tomorrow sometime, so why don't you catch up with that through the recording, and if you have any questions, why don't you contact me over Slack, over private message or something, and then we can, or even Messenger, and I can answer your question. Okay.
All right, sir.
Okay. All right. Any other questions from this particular section that we just did?
I have a question.
Yeah.
When in this proof did we assume we use the fact that one of them is a Carnot engine?
So which is a Kernel Engine?
When in this proof did we assume that the latter one was a Carnot engine, and we use that to prove, one of them is a non-Carnot engine and with a greater efficiency, and the other one is a Carnot engine. So when did we use the idea that it was a Carnot engine?
I see. I guess we used it in the fact that we considered it to be a reversible engine. Because, right, so, but that's a very good question, and this is I think is the correct answer, but, let me also think about it later. But, so if I go back, when we talked about Carnot's engine, we were like, okay, this is Carnot engine, and what we have here is we have a Carnot cycle, which goes like this. But these are all reversible cycles, right? And so this is work here. And because it's a Carnot engine, what we can do is we can reverse. Each part of this cycle is a reversible cycle, right? So we can go in reverse. And if you go in reverse, then this engine essentially runs like so. So, and I think that is where we are using the fact that this is a Carnot engine.
Oh, I see. I think I remember from thermodynamics that if you reverse a Carnot engine, the QH and QC are maintained. But for other reversible engines, they'll have a different QH and QC. So the proof doesn't work.
Right. So, yeah, we don't have to assume that for other engines it doesn't, but that might come out as a corollary. Yeah. Okay. Yeah. So that's where we're using, yeah. And we're using the fact that the efficiency is given by W by QH. Yeah. Okay. Any other
Yeah,
questions?
makes sense.
Okay. So we have about 5 minutes left. I don't want to start a new topic. Thank you. Any more questions or comments about anything else?